Alright, so we're going to start on number 10. Remember, if you're working on something else, just try to keep the volume low enough so those that are working on number 10 can follow along. So we got a child of this weight swinging on a swing. What's the child's gravitational potential energy relative to the lowest position following times? Alright, so we know that potential energy is energy of position. So as this child's position changes, their potential energy is going to change. Probably where I would start off. This is number 10. So as position changes, potential energy also changes. And potential energy gravitationally is due to the gravitational force, which is also depicted right as their weight and height. Since that's the distance in the direction of that force, right? So that's showing you understand that it's gravitational potential we're looking at. And the other part is also showing that you understand that it's the position of the child that's changing, that's what's causing the change in this amount of energy. So the other thing I probably would do in this, and I might do it here in my Y, is draw a picture. So let's do this in red. There's my child on a swing. And they tell me, let's see, those are, for me, 1.8 meters long. And so at some point, the child is up here, right? This is situation A. This is situation B. And this is situation C, and they're telling me that the potential energy gravitationally at this point is 0. So that means my height here is 0. Okay? And let's see, this angle is 33 degrees. So B is actually the more complicated one, being there in between. A and C are pretty straightforward. In fact, I'm going to do C first. P grav at C would be 0. There you go. Because they're telling me in reference to the bottom, which is 0. If we do A, start off with our relationship for gravitational potential energy, the weight times the height. So in A, the weight of this child, my child is 240 newtons. The height above my 0 point is going to be 1.8 meters, and that's solved. Now, for B, the only tricky part is really a geometric tricky part, in that for B, the height would be this distance in here between the lowest position and the upper, and the position it's at. Guys, a little bit quieter, please, a second. And that height is going to be based on that angle. So geometrically, we have this right triangle here and this little extension to it. We know that this angle is 33 degrees. This side is 1.8 meters. This side we'll call H. And we know that this whole side here is also 1.8 meters. So cosine of 33 degrees is adjacent over hypotenuse, h over 1.8 meters. So h equals 1.8 meters cosine 33 degrees. Right? And then the actual height that we want is 1.8 meters minus h for our calculation. And that's this little part down here that's below the triangle. So that's what my height is when I do my calculation here. So it's 240 newtons times that whatever number I get to that 1.8 meters minus h. And that should do it. You should find the maximum at A, the minimum at C, and B is in between it. If you need to help individually on the mathematics or anything, let me know. All right, so we're going to do number 7. And in number 7, we have this sports car accelerating from rest to this. Right away, I start thinking, ooh, they told me the inertia. They told me some speeds. I'm thinking kinetic energy. As soon as they tell me some speeds and inertia, I think kinetic energy. And then they tell me a time. So it doesn't surprise me they ask me for the average power. Since power is the rate that work is done. So this is number 7 here. And I would put things like that. Power is the rate work is done. The kinetic energy is changed, and in this case it's increased by the net work done on the car. So you got this car, its engine's doing work on it through friction of the tires, and that's going into changing the kinetic energy of it. And the power is going to describe the rate that work is done. So mathematically, we have from our equation sheet, the net work is the change in kinetic energy, where that change would be KE final minus KE initial. Its initial kinetic energy we know is 0 because it starts from rest. And then we also know that the power on it is the rate that work is done, so work per time, which in this case is going to equal the net work, which is the KE final, per time. And so we boil that down to 1/2 inertia speed squared over time, or you can even write that betterly as mv squared over 2t. You know the inertia, 1,400 kilograms. It's already in base units, which makes me happy. You know the final velocity, the final speed, 65 kilometers an hour, but you'd want to put that into meters per second. You can do that either using a calculator or using some other reference, or multiplying it by hours per second and kilometers per meter. I'm going to use my calculator just because I don't feel like thinking about it. You want me to show you? Okay. So I'm going to go first to apps. And in apps, I'm going to find, your list is probably going to be shorter than this one because it's a virtual one. What I do is I arrow up to get to the end of my list, because what I'm looking for is a program called SciTools. And for most people, it's right near the end of the list. This one, I have to go up a little bit. But be careful there. You can also use it to improve your other languages, that you probably have it in Spanish and in French. But there it is. Do you find it? Hit enter on that. And then you can go any key. And what we want to use is number 2, which is the unit converter. And the unit we're changing is velocity. So you can either arrow to velocity or hit the number 6. And what you have to do is you put in what you have and then tell it what to convert to. So I'm putting in 65, and then I'm going to arrow my top over to kilometers per hour. And when I hit enter, you can see it's now 65 kilometers per hour. The thing to be careful of is it automatically uses scientific notation. So my 65 became 6.5 times 10 to the 1. And then I arrow my top back to meters per second. And I hit enter. And it tells me, now notice I have that e to the 1. So that's 18.01 or 06. 0.1 or 0.06. So that's what I'm going to use. 65 kilometers per hour, and I'm just going to remind myself that's 18.06 meters per second. And so now I'm just going to substitute in power, 1,400 kilograms, 18.06 meters per second squared over 2. And now I need to check my time, which is in seconds already, 7.4. And that'll be the same for all of us. And that will give me the the amount of power needed from the engine to do this. All right, so we're going to do number 4. Remember, if you're not working on this, that's fine, but just keep it down to those that want to. So number 4, speed of car is increased by this. By what factor is the minimal braking distance increase? 2 miles stays the same. So if we increase the speed, let's see. So this is number 4. If we increase speed, we increase kinetic energy. And the work total changes the kinetic energy. Oh, this is like that interactive lab that you guys did, but you didn't have to pass in. But about half of you passed it, but you didn't have to. So, remember, because as we increase the kinetic energy at the bottom of the ramp, the distance it went kept increasing. So we're expecting this distance to be larger. By what factor will the minimum braking distance be increased? So, what we're looking at here, let's see. For the first situation, we know the work net will equal the change in kinetic energy. And this will be the force through the distance. And this will be KE final minus KE initial. It's going to stop, so that'll be 0. And it'll say the force and the distance that it skids or it brakes that will have to be equal to negative, or the opposite, as the KE it initially has before it starts breaking. The reason it's negative is that amount of energy is decreasing. It's not a directionality. It's the fact that you're getting less energy. So mathematically, we're just going to forget about that negative, because we're going to keep in mind that the force is causing work that's taking energy away. All right? So we're left with F equals 1/2 the inertia, the velocity initial squared. And now we have the new situation where we increase the speed by 25%, and we want to know how is the braking distance increased. So what we're going to do is now say, okay, well, I'm going to do it in green. Now we have the same force. We're going to have, let's call this distance, and we'll call it 2. 1/2, the same inertia. Now rather than V, we're going to have 1.25 V initial squared. 1.25 is an increase of 25%. How did I find the 1.25? Is that the question? Because mine's a 25% increase. So that would mean I'd have the same amount, and I'd increase it by 25%. 25% is 0.25. So I'm interested in how does D2 compare to D1. So I'm just going to do my 1/2 m. Then I'm going to V squared times 1.25 squared. And the reason I did it this way is so I could group these two together and realize that, okay, I could replace those by force parallel, D parallel, because up here in the blue, actually that's what I should probably do. From the blue, I can put in force parallel, D parallel, and from the green, keep my 1.25 squared. And notice that these cancel out. And I'm asked, by what factor will the braking distance? Well, for me it's 1.25 squared. But I think it says, by what does it increase? So if I do this 1.25 and square it, I get that D2 is 1.5625, which means it's increased by 0.5625. Let's see if that's true. Because the 1 would not be an increase. The 1 would be the same. I will put back as soon as I make sure that I'm not having Friday brain on a Thursday. Let's try these. No, that's not nice. Did I put it in right? 5.6. Oh, sorry. 5.6. Helps if you type in the right number. Yes, that didn't help. Putting in the right number. It is looking. I don't love the wording there. By what factor? So the factor they want is the 1.56. That's not really the factor it increased by, but we'll go with what they want. So, yeah, basically, but it's always good to understand why you square that. That's kind of the crux here. Do I understand it? Can I do it again? All right, number 3, very similar to the other ones that we have done. My guess is that some people might have gotten it wrong if they didn't pay attention to their base units. Because they give you the mass in grams and you need to put that in kilograms. And they give you the distance the fielder's glove moves in centimeters when you need to have that in meters if you're going to figure out newtons. So you need to work in base units on this. But it's really a lot of the same ideas here as our other ones, that work changes the energy, and in this case, the net or total work is changing the kinetic energy. And so you're doing W net equals W change in kinetic energy. And the W net is the FD. Change in kinetic energy is going to be KE final minus KE initial. And the final is 0. And now it's really kind of a plug-in. F is what you're looking for. Mine was 0.20 meters. I'm going to forget about that. 1/2 0.145 kilograms. 25 meters per second squared. And then solve for F. Right? Yeah, it's easy on this one. So